Hello students, welcome to Saraswat classes. This is Dr. Sarkar over here and we are solving ISER entrance test year 2019 chemistry section. Question here is, what are the correct orders of bond length dxx and the bond dissociation energy bdexx for F2 and Cl2, where x indicates F and Cl. So theory is that bond dissociation energy, which is BDE, is directly proportional to bond strength, and which is inversely proportional to bond length. So we can predict the order of bond dissociation energy just by considering the bond length ordered. And here we will say that suppose this is the size of a fluorine atom. Okay, this is our fluorine atom. Then this is the size of a chlorine atom. It may appear that when fluorine will combine with each other via covalent bond, where this is the distance dff to begin with, okay, and suppose we consider this is the distance between two Cl, that is the covalent radii. Obviously over here we are saying that is distance Cl. Looking at this diagram, what one can conclude is that dff will be smaller than that of the dCl cell, but that is not the case. Over here we have to consider the repulsions between the lone pair. So suppose this is the ClCl bond to begin with, and this is the FF. Now ClCl bond to begin with is longer in length, so the lone pair repulsions are happening over a larger distance, whereas in a fluorine, which has the same set of lone pairs over the atoms bonded, the lone pair repulsion is happening over a shorter distance. Because of this fact, DFF, the distance DFF becomes greater than the distance ClCl. If that is the case, then what we will say about the bond dissociation energy? That BDE ClCl will be greater than the BDE FF. So by taking into consideration the repulsions between the lone pair of each bonded atom, in which the fluorine is lying at a shorter distance initially, so the repulsion is more, the distance between these two fluorine atoms, they increase. Okay, but such repulsion between these are not so big or heavy, because these two chlorine atoms to begin with are lying at a higher distance. So that means our answer over here is going to be D. Next question is given, which is the the next question is, which is the appropriate combination of spin configuration and color for the anionic complex COL6 3-, where L is a monodentate and monoanionic ligand, and we have been given 4 options over here. So for answering this question, the theory is that we always observe the complementary color of the complex. Okay, that is what we see, which means what? So for this we will need to consider a color wheel, and I will make some divisions within it. Okay, and suppose let's begin from V, that is violet. If this region is violet, the next region will be blue in color. Okay, just like your whip jaw. So this is your blue in color. Okay, then that will be followed by the green color. Okay, which will be followed by the yellow color. That means something that looks violet is absorbing yellow color. Okay, then it will be followed by orange color, which means something that is looking orange is absorbing blue color. And finally we will have the red, which is obviously this one. So this is our color wheel, and that helps us to remember the complementary colors. So violet absorbing yellow, blue absorbing orange, looks green absorbing red, looks yellow absorbing violet, and that is how we have to remember. Now in the given options over here, let us make a table. So it says, we will say color, that is the appearance, then we will say absorbs, obviously we will talk in terms of wavelength, and then finally we have the energy gap, which is an indicator whether it is a high spin or low spin complex. So when we have, let me say this, energy gap high, we have high spin, low spin complex, which means that out here delta O is higher than that of pairing energy. When we have energy gap low, it means high spin complex. That means pairing energy is greater than that of delta O. So keeping these facts in mind, and now using the table, besides that we have to remember, it's a very vital point, that energy is inversely proportional to lambda. So out here if we have green, something that looks green, then obviously we will say it is red. Okay, absorbing red. So red means high wavelength. Red means high wavelength. That is something around 570 nanometer to 650 nanometer. Okay, and this is around 580 nanometer. This is around 560 nanometer. This is 490 nanometer, and this is say around 430. And that marker over here, the lower marker out here, is around 400 nanometer. So that is the range. So whenever we are talking about a red spectrum, it will be lying between 650 to 750. Within that range, the red color and its varied wavelengths will rise. Okay. So red means obviously we are talking about if it is absorbing red, that means the energy gap is very low. Okay. So energy gap is less, and obviously we will say it is a high spin complex. Similarly, next one it is given green and it says red. Okay. Because the energy gas gap is less, so this should be actually again high spin, but in the option it is given, if you check, it is given low spin. So obviously that is not possible. So we will say this is wrong. Okay. If they are saying low spin, then it is wrong. Next one they are saying blue, that means it is obviously absorbing orange. Okay. And orange is what, very much close to red, lying within the range of 650 to 580 nanometer. That means again energy gap is less, and they are saying it should be low spin, but it should be actually high spin. So this is again wrong. Next one they say it is yellow. Okay, so if it is yellow, it is absorbing what? Violet. That means energy gap is very high. Okay, high energy gap. So actually it should be low spin, but in the option they are giving it has to be as high spin. So again, if it is they are saying high spin, then it is wrong. So the only correct option out here for this question will be option A. Next question they are saying, which is a memory based question, which of the following combination of elements form interstitial hydrides? So basically one has to remember that D and F block elements, they form interstitial hydrides. Boron and aluminum will form covalent hydrides. Sodium and magnesium will form salt-like hydrides. Okay, these will form salt-like hydrides. Okay, they will be forming covalent hydrides, and for that reason they cannot be our chosen option. Next question they are saying, how many geometrical isomers are possible for a square planar complex PD? PY means pyridine, Cl means chlorine, Br means bromine, and they have NH3. So if you look at this complex, it is basically of the type M, A, B, C, D complex. Okay. This is N value can be 0, it can be positive or negative. That is what is the indication over here. So out here, the possible arrangements can be found out just fixing one of the positions of the ligands. So let's keep A, let's say B, C and D. So this is one possible position or arrangement possible. Keeping A as fixed again, just interchange, okay, the position of B with C. So we have C out here and B here. So in respect to A, B is trans. Again we have plus minus 0. The other one we will say opposite to A, we can now keep a D. Doesn't matter where you put B or C. So that way now we can see there are possibility of 3 such geometrical isomers, and our answer over here is going to be option 3. Question number 20 is, over here a molecular adduct is formed between BF3 and ether Which of the following values describe the coordination number, valency, and oxidation state of B within the adduct? So for this, one has to first draw the structure of BF3, which is obviously a trigonal planar structure. Okay, and so this is the, yeah, let me just go back. Okay, so this is the trigonal plane out here, and mind you, this is the vacant p orbital in the B. Okay, it is a hypovalent molecule, okay, which does not obey the octet rule. Now, if you have the, yeah, let's go back to the, if you consider the OET, which is diethyl ether, is having two such lone pairs on oxygen, which is going to get donated over here. So finally, in the adduct, we can write it like this: B F3 we will have sp3 hybridization. This is the coordinate bond. So basically B is now surrounded by 4 atoms. Okay. So we will say its coordination number should be equal to 4. What is the valency of boron? Valency of boron obviously will be the number of bonds it forms, okay, or a capability of forming number of bonds. And obviously valency is the boron is having already only 3 electrons, okay, so it can form 3 covalent bonds. Okay, the other one can be a coordinate bond. Okay, so out here we will say the valency of boron in the structure is going to be 3. And when it comes to oxidation state, obviously we will say over here the oxidation state of the boron, because of these electronegative atoms, okay, it is going to be 3, and we should write rather plus 3. Okay, so from that we will say the answer over here is going to be C. Now oxidation coordination number can never be 3, so this option D is never going to be correct. Okay, coordination number will always be 4, so we have to choose from the above 3 options A, B or C, in which valency can never be 4. That is why we are not using or selecting A as the option. Now when you have to choose between B and C, alright, we have to understand that the donation, whenever the donation is happening from the oxygen to the boron, okay, this will be having some delta positive charge, and this will be having some delta negative charge. Okay, so that is why whenever we have to calculate the oxidation state, we have to keep boron as a neutral, and then think of that each of these fluorine atoms, they are having -1 or uninegative charge, and that is why if you take this to be as X and these to be as -1, -1 and -1, then X -3 equal to 0, so therefore you will say X is going to be +3. Alright. Question number 21 is, while making cottage cheese or paneer from a milk by adding dilute acetic acid, the milk proteins undergo. This is again a memory based question, and where we will say it is undergoing denaturation of proteins. Okay, and this is obviously a irreversible process. Okay, in the next question 22, what is the final major product of the following reaction? So this reaction is basically a elimination reaction. Okay, so initially what is happening, we have the benzene, suppose like that. Okay, and now you have used the first reagent, that is KOH in presence of OET. So this OET will be acting as a base, all right, and it will take up one of the acidic protons. Okay, like that, and in the process elimination will take place, and that will lead to the formation of a trans type of an alkene, something like that, which will undergo further elimination in presence of a stronger base called sodium amide. Okay, and this will finally lead to the formation of the alkyne product, which is something like that. Okay, so the first step out here is the elimination E2 process, and in the presence of a stronger base, okay, it will further lose the HBr to form the alkyne. Next we have the question from aromatic chemistry. We have identified the final major product in the following reaction sequence. So initially out here, this is given to be as benzamide in the presence of Br2. It says ethanolic KOH, that means KOH is dissolved in ethanol. This is undergoing basically Hoffman rearrangement. Okay, and in the process benzamide will get converted to amine or aniline. Okay, aniline, if you treat it with excess amount of Br2 in presence of water, it will undergo electrophilic aromatic substitution reactions. Okay, because aniline is having plus M effect and makes the ring highly electron rich. So both all the 2, 6, 4 positions will be now substituted via bromine, and the product that will be formed will be having this type of a structure, and hence A will be our answer over here. Next, we have been given the question, identify the compound X, which is this, in the following reaction. So out here we have been given benzene diazonium chloride, which is N2 plus Cl minus, and we have been given the ethanol and it is forming benzene, and it is saying it is also forming X. Nitrogen is getting released. Okay, so there has been some abstraction of H. Okay, abstraction of H from this molecule. So if abstraction of H from this molecule happens, what can one can say is that suppose in this reaction mechanism there is a formation of the positively charged ion, or there is a radical formation over here under these conditions. Okay, so what can happen out here is that a H will be abstracted. A H will be abstracted. How? There is an electron out here like that. Okay, I'm also mentioning this one. So suppose, let us suppose that this has been created on heating. Okay, then this dot will accept that dot. Okay, and that dot goes in here, that comes in there, and that goes out like that. Okay, so ultimately we are having what? We are having this product. Okay, sorry, we are having this product, that is the benzene, and along with that, if this mechanism operates, we will say the product formed out here is going to be acetaldehyde, which is CH3CHO. In the next, we have been given which one of the following compounds is aromatic. So for that, we call systems aromatic when they follow these conditions. They are cyclic, conjugated, they are planar, and follow the 4n plus 2 pi electron rule, where n has the value 0, 1, 2, 3, and so on. Okay. We will be calling systems anti-aromatic when they are cyclic, even they are also conjugated, they too are planar, but they are following 4n pi electron rule. Okay, we will be calling systems non-aromatic when any of the conditions are fulfilled. They are non-cyclic, they are non-planar, non-conjugated, that is, has sp3 carbon. Now, if you observe closely out here, the first molecule here, it is having a sp3 carbon. Okay, so obviously we will call this as non-aromatic. Okay, we will call this as non-aromatic. Na means non-aromatic, A means aromatic, and AA we will use as anti-aromatic. Even this system, if you check this carbon, this is again sp3. So this we will again say it is non-aromatic. What about that one? This is a 6 pi electron system. Is it cyclic? Yes, cyclic. Is it conjugated? Yes, it is conjugated. Is it planar? It is planar. Is it following the 4n plus 2 rule? Yes, it is a 6 pi electron system. So this is our aromatic. What about this molecule? Actually, this will be existing in a tub shape structure to avoid anti-aromaticity. And so now because it is having a tub shape, it is becoming non-aromatic. So this too will be non-aromatic. So the only aromatic system out here is going to be option C. Okay, so next question out here is what? Using the Arrhenius equation, find out the value of K at t equal to infinity. Now what is our Arrhenius equation? Rate constant K is equal to A, that is the Arrhenius constant, e to the power EA, that is the activation energy, divided by RT. Now condition out here is T is going to infinity. Then what happens to the equation 1, which is the Arrhenius equation? We will say A e to the power EA R infinity. So that will mean what? That K we will write as A e to the power 0, and that means K can be written as equal to A, and obviously our answer over here is going to be option A. Okay, next, what we have been given. Which one of the following is not an example of heterogeneous equilibrium? Let's write the equations. Equilibrium between water and water vapor in a closed container. So we have liquid water, sorry, water vapor. So it is going to be gaseous, reversible arrow, H2O liquid. These two are different phases, so it is heterogeneous system, that is in equilibrium. Next we have CH3, COO, CH3, sorry, CH3, COO, CH2, CH3, that is ethyl acetate. So it says equilibrium attained during acid hydrolysis, acid catalyzed hydrolysis of ethyl acetate. So this is, we know, a liquid. We have given catalytic amount of H plus, for which this is undergoing hydrolysis. So this is also a liquid, and sorry, the other molecule will be CH3, CH2OH, which is also a liquid. So these all are liquid, so hence it is not a heterogeneous system that is in equilibrium, rather it is a homogeneous system that is in equilibrium. Option C says equilibrium between solid calcium hydroxide and its saturated solution. So they are saying solid calcium hydroxide, we have Ca2 plus and 2OH minus. So these are in the aqueous phase, whereas this is solid, so it is again a heterogeneous equilibrium. We have calcium carbonate, that is obviously a solid. We have CO2, which is gas, and we have calcium oxide, which is a solid. So this is again example of a heterogeneous equilibrium. So out here it says which one of the following is not an example of heterogeneous equilibrium. So obviously we will say one that is homogeneous equilibrium. What is the homogeneous equilibrium? This is the homogeneous equilibrium. That should be our answer. Over here, it is given at 60 degrees centigrade, 50% of N2O4 gas is going to 2NO2 gas. What is the standard Gibbs free energy change at 60 degrees centigrade and 1 atmospheric pressure for this process? We have to find out. They are saying 50% of this, right? That means if it is given initially 1 atm and this is 0 at equilibrium, what we will say? 1 minus 0.5 and this will be 2 into 0.5. Total number of moles at equilibrium, what is that? 0.5 atm, sorry, 0.5 and this will be 1. So it is going to be 1.5 moles. Okay. Okay, in this question, it is asked at 60 degrees centigrade, 50% of N2O4 gas is dissociated to NO2. What is the standard Gibbs free energy change at 60 degrees centigrade and at 1 atmospheric pressure for the process? So over here we are having N2O4, which is a gas, and it is dissociating to form 2NO2 gas. Okay, so initially this is 1 atm and that is equal to 0. At equilibrium, this is 1 atm. If this is 50% dissociation, then that is 0.5 and that should be 2 into 0.5. That means this is 1 mole and that is 0.5 mole. Total number of moles at equilibrium is equal to 0.5 plus 1, that is 1.5 moles. So out here when we say the partial pressure, that is of N2O4, it will be mole fraction into total pressure P, and that is going to be what? It is going to be 0.5 by 1.5 into 1 atm, which is the total pressure. So that stands out to be what? It is going to be basically 1 by 3 atm. Similarly, for PNO2, it is going to be X into P. So this is X for what? N2O4. This is X for what? NO2. So this will be what? 1 by 1.5 into 1 ATM, and that will be what? Basically 10 by 15, that means it is going to be 2 by 3 ATM. Now what is the KP out here? It is going to be PNO2 by PN2O4, PNO2 square by PN2O4, so that is going to be basically 2 by 3 square into 3 by 1, or that will be basically 4 by 3 ATM, that is the KP. So when we want to calculate delta G, we have to remember that it is minus RT ln KP, or that will be what? We will say 8.314 into 333 Kelvin into ln 4 by 3, and once we do the math, we will say it is going to be 8.314 into 33 into ln 4 divided by 3, and that will come out to be 796. So it is going to be minus 796.46, okay, joules per mole inverse. So our answer over here is basically going to be this one, okay. All right, for the next question, we have been asked for a cell AG plus comma Cl salt bridge AgCl solid Ag. That means this is the cell. Over here the E reduction of the half cells, okay, it is E reduction. Please understand, it is E reduction. So it will be, for E cell we will use the E cathode minus E anode. Then this is given to be 0.79, and this is my 0.22. So out here, if you have to find out which is the cathode and anode, so this is your anode and that is your cathode, okay. That is what has to be beared in mind. So if that is the cathode, this is the cathode and this is the anode, so for our calculation, okay, what we will say, this is our anode reduction potential and this is our cathode reduction potential, okay. So out here what we will do, we will write E cell is equal to E naught cell RT NF ln K, okay, at equilibrium. We know delta G is equal to 0, so E cell also will be equal to 0. And what is our E cell over here? E naught cell, E cathode reduction potential minus E anode reduction potential, okay. So that will come out to be as 0.22 minus 0.79, so that is minus 0.57, voltage. Okay, now from this equation say 1, we will have now E naught cell, okay, will be equal to RT NF ln K. For this we have to find out the value of ln K. So if we rearrange, we will say it is going to be NFE naught cell by RT, and if you put the values, it is 96485, 0 point minus 0.57 divided by 1.34 into 298 Kelvin, and this will come out to be minus 0.22197, and that should be our answer. That is option A is the correct answer. Out here in this question, germanium doped indium. Okay, so we have a germanium, suppose like this. Okay, so these are all germanium. Germanium has the valency 4. So all these are interlinked like this, okay, suppose, and they are neutral. Okay, now if you dope this one germanium with indium, okay, suppose there is an indium over here. So for each germanium there was like this, there was bonding. Okay, okay, like that. Now whenever you have indium, so indium has 3 electrons. Okay, indium has 3 electrons. That means what? One such electron, over here one electron, here one electron, and here we have a, say, a hole, something like that. But there is a, so basically because of indium, as you can see for germanium there are all 4 electrons, so there is no creation of hole. But whenever there is a indium in place of a germanium, this is the indium in place of germanium, because there is one side that is vacant, there is a creation of a hole. Okay, this is a hole, and this will be our charge carrier. So this will be called as a p-type semiconductor. Okay, semiconductor. Using the same principle, in another place I'm showing. Okay, now similar picture you think, and now suppose I am removing this one, or let's say let us keep this one over here. Let's draw a fresh diagram. Okay, or let's use this one only. Suppose here we have, say, another different type of a doping, and say this one, this green one. Okay, over here, this is my, over here I am saying, suppose this is silicon now, this is silicon now, and silicon also has valency 4. All these red atoms are silicon, all the red atoms are silicon. Okay, so you have understood p-type. Right now we are doing the, for the silicon. Now all the red atoms are silicon. Let's consider this way, all the red atoms are silicon. Okay, let us remove this part. So Out here, this is the N atom over here, okay? Suppose this is the N doping. Now, when N doping happens, N has 5 valence electrons. That means what? 4 will be there. Apart from that, one more extra will be there. So, this one more extra will make this as a negative. So, this is a negative charge. So, this becomes a N type semiconductor. So, in the previous one, I have explained P type semiconductor and now N type semiconductor. That means we will say for this one, two option, it will be a N type semiconductor. For germanium doped with indium, we will say it is a P type semiconductor. Okay. For ZNS, it is a memory based question. This will be your Frankel defect. And for CSL, it will be your Schottky defect. That way, if we judge, we will say one for one we are having P type semiconductor. That means for option 1, Roman 1, we are having numerical 3. For 2, we are having 1. For ZNS, we are having Frankel defect. So option D is the correct option over here. Thanks for listening. Keep visiting Saurabh classes for the solution of IAT 2021 paper that was being asked on 17th of this month, that is September. Thanks for listening. Keep visiting the classes. Have a great day.